Greetings and welcome to the Chemistry 223 Organic Chemistry Lab, where we're going to go over what is definitely the largest part of all chemistry. Chemistry is subdivided into several subsections, but organic chemistry is where most of chemistry happens in the world. Most chemists, if you look around the world, are organic or one of their related areas. So that would include things like biochemistry, medicinal chemistry, stuff like that. So organic chemistry is a big part of everything around us. But most of the time in first year classes, organic chemistry is completely ignored. And that worked out to be a really bad thing for me. When I went to the beginning of organic chemistry, which is usually the second year chemistry class, if you're a major in chemistry, I was feeling pretty confident. I'd been through the Chem 221, Chem 222, Chem 223 equivalent series at the college I was at. And I thought, yeah, I can handle this, no problem. And man, I came in and I was literally snowed over. I had no idea what was going on. It was completely foreign to me after what I'd been through in the 221 through 223 series. In addition, there were several things that I thought I knew what they were, and they weren't. They sound very similar. So like alkane, alkene, alkyne sound very, very similar, but they're different. Also, there's compounds like methanol and methanal, and subtle pronunciations make a big difference in reactivity. So the goal of this section, besides just learning organic chemistry, which is kind of interesting unto itself, but the real goal is that, man, if you're going to take organic chemistry one day, I don't want you to go through what happened to me, all right? I want you to be prepared and know at least the foundations of how this stuff all works, so that you won't have this literally snow-blinded effect, which happened to me. The beginning of organic chemistry was kind of tough academically for me, but I got through it and conquered it and went on, and boy, now I'm teaching it. Woohoo! Anyway, the little things like that still make me kind of happy. But anyway, the goal of this is just to introduce you to organic chemistry. Now, if you're going to take organic chemistry, this will be really cool. If you're not planning on taking organic chemistry, and a lot of majors you don't need to take organic chemistry, this will still have usefulness to you. A lot of the things that you use in your day-to-day life are based on chemicals we're going to talk about. It's another kind of naming and systematic approach to different compounds, and we'll look at that so you'll be better prepared when next time you go to the store or stuff like that. Oh boy. Organic chemistry is typically a second-year chemistry course. It's the course that you would take most of the time right after Chem 221 through Chem 223, all right? But even people that aren't going to take organic chemistry, there is definitely some reasons why exposure to this area will make it better. You'll find reference to this in the news, and you'll see it in pop media and movies and stuff like that. So having a little experience how this stuff works is going to help you regardless of what your plans are, trust me. This lab is going to focus mostly on the nomenclature, the naming of organic chemistry compounds, all right? I want you to see how they're built, what they're made from, and how these names kind of work, all right? In lecture, I will go over some of the organic chemical reactions so you can get a sense of what that part of OChem is like. That's actually the bigger part of organic chemistry, but that's way beyond what we can do in basically 1 week in Chem 222. So we'll look at naming. In lecture, I'll show you some reactions, and just realize that in the actual organic chemistry class, you will look at the naming in more detail, but you'll certainly look a lot more at the reactions, like how you make it, what you can react it with if you do have it, stuff like that. It will be helpful for you to have the geometry and polarity guide. And again, it's in your companion, it's online. You can get it there at mhchem.org/geopo. That's the same guide we've used in the last 2 labs. Also for this lab, I do recommend the Organic Chemistry Guide, the nomenclature guide. That's available at mhchem.org/OCG, Organic Chemistry Guide. The front page down there is shown in the lower left. It shows what we're going to talk about here in a little bit, the alkyl groups. And I definitely also recommend you go through the lecture notes, stuff like that. Organic chemistry is basically built along what are called alkyl groups. And alkyl groups was something that was quite fascinating to me, but something I had no background in before I went into the class. So an alkyl group is like a building block. It's like a one piece of Lego, if you're into Legos at all, if you've ever done Legos, like, one Lego block, woohoo. But if you take a whole bunch of Lego blocks and put them together, you can make R2-D2 or, the Death Star, or all these kind of cool things they have in Legos. But anyway, alkyl groups by themselves are not compounds. And I have in the upper left-hand corner there pictures of the first three. A methyl group, all right, is a single carbon. And as we've seen since the beginning of Chem 222, carbon loves to have 4 bonds. So 3 of the 4 bonds are connected to hydrogens. But that 4th bond with that little squiggly line, that's going to have to be connected to something else to make a compound. So methyl is not a compound unto itself, but methyl is a building block, we're going to see, of other kinds of compounds. Notice here the methyl group, it's sp3 hybridized, it's tetrahedral, it's 109, all that kind of jazz. That'll be important later on. Now, if you take another of these sp3 carbons, which means carbons that wants 4 bonds, and you connect it to the methyl, now you have 2 carbons in a row, and again, all spots are taken by a hydrogen except for 1, then you end up with the ethyl group. And the ethyl group is just the good old methyl group with another carbon next to it. And if you take another sp3 tetrahedral carbon and put it on the end of the ethyl group, now you have 3 carbons in a row. This is what's called the propyl group. So you can see that going from methyl to ethyl, you just added another carbon, an sp3 hybridized carbon. Going from ethyl to propyl, you add another sp3 hybridized carbon. If you look in that list down below, after propyl, you end up with a butyl, and after butyl is pentyl, hexyl, heptyl, octyl, nonyl. Yes, they do go beyond that, but for Chem 222, that's a great amount. All of these, again, are not compounds, all right? They're missing something. So in the methyl group, you can see here in this little picture, there's like a spot missing right there. There's nothing connected. And the same thing for ethyl and propyl and stuff like that. So alkyl groups are the building blocks. All right, you can put alkyl groups together to make a compound. You can put alkyl groups with oxygen and stuff, but you have to put them with something else. And when you do this, when you take alkyl groups and you put them with something else, you end up with some of the classes of organic compounds. Classes are sometimes called families, and we'll talk about these as we go through. It's all of these families or classes are just some way to put alkyl groups together with something else to make a compound. Often in organic chemistry, you're going to see the generic capital R, and that just means it's any random alkyl group. And you'll see why this is useful here in a little bit. So if I put R next to an H, that would be an alkyl group connected to a hydrogen. And the alkyl group could be ethyl, methyl, propyl, butyl, pentyl, hexyl, heptyl, octyl, nonyl, or any of the other ones that are out there. It's just some random alkyl group connected, in this case, to hydrogen. And we'll see this here coming up. So knowing the alkyl groups is really cool. It makes your life a lot easier. If you have the organic chemistry nomenclature guide next to you, you've got that list and you'll be good to go. So the simplest of all the compounds, of all the families in organic chemistry, is called an alkane. Now, alkyl groups weren't compounds. Alkanes are compounds. So to make an alkane, look in the upper left-hand corner, you're going to take some random alkyl group R and just put a hydrogen on the end, all right? If you put a hydrogen on the end, those sp3 hybridized carbons then have their filled octet, 4 bonds, and they're totally happy. So an alkane is just an alkyl group with a hydrogen. All of the alkanes have a general formula. It's CnH2n plus 2, and N is the number of carbons. I'll talk about that more in a little bit, but this is a nice way to recognize if a certain compound is an alkane. Now, to name these crazy alkanes, all right, you start with the alkyl group and you take off the YL and you add ANE. So we saw earlier that methyl was the CH3 group. Well, if we're going to make an alkane out of it, we're going to turn that CH3 into CH4. We're going to add a hydrogen to it. So methyl minus YL plus ANE, that's methane, all right? Methane, CH4, which we've danced around in Chem 222 so far. Methane is the main ingredient in natural gas. So if you have a natural gas heating system or maybe an oven, something like that, you're probably burning mostly methane. Methane is the simplest of the alkanes. Again, it's a methyl group plus a hydrogen. If you take the ethyl group, which was CH3CH2, and you add a hydrogen to that, you make what's called ethane. So ethyl minus YL is eth plus A-N-E, ethane, okay? Ethane is C2H6. Ethyl was C2H5. We put a H on the end of it, C2H6, all right? On the right side is propane. Propane is a propyl group with 3 carbons and 7 hydrogens. You put a hydrogen on the end, then you have 8 hydrogens total. That's propane. Propane is what most people use when they barbecue outside. It's usually a propane burner that happens. Now let's go back to the formula up there, the CnH2n plus 2. For methane, the N was 1. So 1 times 2 plus 2 is 4. Aha! 4 hydrogens for every 1 carbon. On ethane, you have N of 2 carbon atoms. So 2 times 2, 4, plus 2, 6 hydrogens. So you can see how ethane, C2H6. Propane with N of 3 will have 8 hydrogens, etc., etc. So if you had an 100 carbon alkane, then the number of hydrogens you'd need would be 2 times 100 plus 2. You'd have to have 202 hydrogens for every 100 carbons if it's going to be an alkane. And we're going to see that not everything is alkane. Sometimes alkanes are called saturated because every carbon has just single bonds around it, just single bonds to hydrogens. There's no oxygens, there's no double bonds, no nitrogen, stuff like that. And again, all the carbons in alkanes are sp3 hybridized. You can go past propane though. Butane would have 4 carbons, and normally you would take the butyl group, which is C4H9, and you would put a hydrogen on the end of it to make what we would think is butane. But there's a problem when you get to butane, because the formula for butane, C4H10. Well, C4H10, which most people see right away, you can put the 4 carbons in a long chain, like 4 carbons in a row is what I'll call a chain, okay? And put hydrogens all the way around the outside, and that's awesome. If you have just a straight chain of carbon atoms, you put the little N in front of it. So this thing here is called N-butane. However, you can also make an isomer. You can put a methyl group, remember CH3 is methyl, a methyl group off the second carbon of 3 carbons. And what you're basically doing here is in the N-butane over there, you're taking this CH3 and swapping it with this hydrogen. So the hydrogen is now on the end and the CH3 is in the middle, all right? So same number of atoms and same type of atoms, but different configurations. This is what an isomer is. And isomers are a big part of organic chemistry. And again, this kind of blew my mind when I went into it. So the compound on the right with 4 carbons in a row, that's called N-butane. The N, I guess, stands for normal, if you will. But the other one, what you want to do is you want to call it by the longest chain of carbons with the smallest number possible. So look at the name, it's 2-methylpropane. So the number of carbons in a row, let me use a different color, would be 3. All right, I'm going to circle the 3 carbons right there. And if that methyl group wasn't there and there was a hydrogen, it would be a propane. However, it's not a hydrogen, obviously, it's a methyl group. So if you count left to right, 1, 2, 3, that methyl group is off the second carbon. So we would call this 2-methylpropane. The methyl group is off the second carbon. Now, it might be tempting to think that you could have a 1-methylpropane, but that would be, if you go back to the N-butane, you would just flip these 2 right here, all right? And then you'd have 4 carbons in a row. It would not be an isomer. That would be just N-butane rotating the bonds around a little bit. If you can rotate the bonds but not break them and get to the other form, then it's not an isomer. I cannot rotate N-butane into 2-methylpropane without physically breaking the bonds that hold them together. So that's what makes the isomer the isomer. Pentane has 5 carbons. So when you plug a little hydrogen on the end, then you have 12 hydrogens total. If you have all 5 carbons in a row with hydrogens all the way around the outside, that's N-pentane. But this thing actually has 2 isomers. The first one is kind of like the 2-methylpropane we saw with the butane. This would be 2-methylbutane. And if you look at that numbering system, at first it might feel like a 3. Here's what I mean. I'm going to count on the bottom. 1, 2, 3, 4. And if we're trying to find a number for this one, you can see by the blue numbers, it looks like that would be a 3-methylbutane. But in organic chemistry, smallest number is really, really important. So what I recommend when you're learning organic chemistry is that you count not only left to right, which is what I did, and that's what people in the United States do because everybody reads left to right in our country, but you also count right to left. So above it now, I'm going to have a 1, 2, 3, 4. And you can see using the red numbers, you can also call this compound 2-methylbutane. So this compound you could call 2-methylbutane or 3-methylbutane. You need to call it 2-methylbutane because 2 is smaller than 3, okay? So, oh boy. So counting left to right and right to left is really important, especially when you're learning this, okay? And use different colors like I did or whatever you need to, but definitely check that out. You could also call this compound by yet a different name. If you would have your longest chain of 3 carbon atoms, that would be a propane. And you'd have essentially an ethyl group off the propane. That's ethyl group would be CH3CH2. So you could also call this a 2-ethyl propane. But in organic chemistry, in addition to smallest number, which we just talked about, you also want to have longest chain of carbon atoms. So the longest chain in the molecule I circled there with gold, the longest chain is just 3 carbons. And that is definitely inferior to the way when we had 4 carbons. That's the butane. So longest chain, 4 carbons is better than 3 carbons. Smallest number, 2 is better than 3. So in this molecule, all right, you call it, the best way to call it would be 2-methylbutane. Smallest number, longest chain, okay? If you called it 3-methylbutane or 2-ethylpropane, it would be like, oh, I ain't knowing what you're talking about. Like, you know what I'm saying, but it's like kind of like lame and it sounds like you're, not very educated or something. So, so smallest number, longest chain, super, super important. The third isomer in the lower left-hand corner, the longest chain, and you can circle it any way you want to, by the way, the longest chain is going to be 3 carbons. Now, if you circled left to right, that's fine too. It's still 3 carbons, doesn't matter which one you do. And off whatever 3 carbons you circled, then you have a methyl group right there and a methyl group right there. So this is a dimethylpropane, all right? Di means 2. It's one of the Greek prefixes we used in Chem 221. And we're going to see in a little bit that each of those pieces not in the chain, it needs its own number. So you call it 2,2 dimethylpropane. Each methyl group gets its own number, and that'll be important here coming up a little bit. So the number of isomers gets a little crazier the more carbons you get to it, but again, just remember, longest chain, smallest number. If you take your alkane and instead of just putting hydrogens on the end, you can actually pull the hydrogens off and make that into what's called a cycloalkane. A cycloalkane is literally a chain of carbon atoms in literally like a circle, or in like a cyclic system. And this is also all sp3 hybridized carbons, but they're a little bit different than alkanes. So a cycloalkane is actually another family or class of organic chemistry compounds. It also is based on the alkyl groups. The names you're going to see come from them, but it's a little bit different. So if you want to have a 3-carbon chain in the one in the lower left-hand corner of the screen, then this becomes not propane, but cyclopropane. So because propyl group had 3 carbons, and there's 3 carbons in this structure, you would take the YL off, add A and E, but before all of that, put a cyclo. So this is cyclopropane. And you can see the next one over there is cyclobutane, followed by cyclopentane, cyclohexane, etc., etc. Now, the formula for a cycloalkane is different than the formula for an alkane. Alkanes are CnH2n plus 2. Cycloalkanes, CnH2n. Because they have different number of hydrogens, i.e. cycloalkane was just H2n and regular alkanes are H2n plus 2, cycloalkanes are not isomers of alkanes, different numbers of atoms. So propane and cyclopropane are not isomers. They have different numbers of hydrogens in them, and that's enough to make them different. Now, reactivity-wise, they are very similar. There's a few different things that cycloalkanes will do that regular alkanes won't, but generally speaking, all of these are just really good fuels. You can burn them. People that study cycloalkanes would probably get mad at me for saying that, but anyway, there's some differences, but not as many as some of the other groups we're going to see coming up. So far, we've looked at only adding hydrogens to alkanes, or taking off hydrogens for that matter. There's another class of compounds called alkyl halides. And an alkyl halide, you take the general alkyl group R, but you add a halogen to it, X, all right? And X, most of the time, will be fluorine, chlorine, bromine, or iodine, the 4 most common of the halogens. And these are also very common. Now, the formula is a little bit messier. You have a total of 2n plus 2 spots around the carbons, but some of them will be taken up by the halogens. So if you have Y halogens, Y X's, then 2n plus 2 minus Y will be the number of hydrogens. Don't get real lost in that, but that's the idea. Down in the lower left-hand corner is chloromethane. And what they did is they took regular methane, which is CH4, they pulled one of the hydrogens off and put a chlorine in there. So if you're going to name this, it's like haloalkane. So in this case, it would be chloro, because chloro is the halo halogen, and you'd put that on the methane, chloromethane. Chloromethane is also known as methyl chloride. You'll see it both ways. If you're going to put 2 bromines off an ethane, you end up with 2 different isomers. The isomer on the left, where there's a bromine on the left carbon and the right carbon, that's 1,2 dibromoethane. So 2 carbons like that would be ethane if they were all hydrogens, but we have 2 bromines, dibromo, and in this case, the one is off the first carbon and the other bromine's off the second carbon. So 1,2 dibromoethane. Look at the structure right next to it. That's also a dibromoethane, but that one has bromines, both of them off the same carbon. That compound is 1,1-dibromoethane. All right, so you can see here how the numbers become pretty important, man. You wouldn't want to call it 2,2-dibromoethane because, oh, those are bigger numbers than 1,1-dibromoethane, but you get the idea, okay? Notice how we're beginning to lose the lone pairs more and more on these things. Lone pairs in organic chemistry often aren't shown. The hip chemist knows, for example, in those bromines, that there would be 3 lone pairs of electrons around them. Same thing with the chlorine and the chloromethane over there in the corner. So just realize we're starting to get into higher levels. We're going to start seeing things get a little strange. In the right-hand side there, that compound is 1 1112 tetrafluoroethane. So it's ethane because there's 2 carbons, and there are a total of 4 fluorines. 3 of them are off the first carbon, and the last one is off the second one. So 1112 tetrafluoroethane. That's actually one of the CFCs. If you're an environmentalist, they talk about CFCs. They can be kind of bad news. That's one of the ones that has been used a lot in the past. So anyway, there's lots of examples with it. We're seeing here examples with chlorine, bromine, and fluorine. There are definitely examples with iodine as well. So just kind of keep your eyes open. An alkene is similar to an alkane, but with one really important difference. An alkene has a double bond, all right? And remember, a double bond is a sigma plus pi to make 2 bonds, all right? Double bonds are much more reactive than single bonds generally. And so people make a big deal about having alkenes and what they can do with them. So alkene, again, is just different from an alkane because you have at least one double bond. And the second bond, the pi bond, is a little bit more reactive. And so there's more things you can do with it. It becomes really important. There's different names for some of the alkenes, and I'm going to show you a couple different ways to name them. When I took organic chemistry back in the day, there was just the one version, but now as organic chemistry gets more sophisticated, they're changing it a little bit, and honestly for some good reasons, I understand, but I'm going to show you some examples. So in the lower left side, the middle left side, I guess, 2 carbons with a double bond between them. Instead of ethane, which would be the alkane name, this would be called ethene. So ethene is just 2 carbons with a double bond in the middle. Remember that ethane was carbon-carbon single bonds with more hydrogens around. Ethene tells the chemist that, I've got a double bond in there. Ethene is also known as ethylene. So if you've heard about ethylene, ethylene and ethene are the same thing. Ethene is the formal name, ethylene is the common name. This is similar to dihydrogen monoxide, the official name for water versus water. Nobody but nerdy chemists, hand raised, talks about it as DHMO, dihydrogen monoxide. Everybody talks about it as water. You get the idea. Under ethene is propene. Propene is like propane, 3 carbons, but again, the ene means there's a double bond. Propene has a double bond, and propene is also known as propylene. Now, when you end up with 4 carbons, you end up with lots of types of isomers. The first one up there in the upper left-hand corner, which is 1-butene, that just has the double bond beginning at the first carbon, all right? And that one I don't think is too strange. So notice that the 1 of 1-butene refers to the fact that it's starting on the first carbon. That's where the double bond is. The newer way of calling 1-butene is but-1-ene. So notice how they put the 1 between the but and the ene, and there's reasons for that you'll see in organic chemistry. I find it a little more awkward, but I do understand why they're doing it. So you'll see it both ways probably if you take organic chemistry. But the next one is even more interesting. If you move the double bond to the second carbon, so there's a double bond between the second and the third carbon, it becomes 2-butene. But notice that there's this additional trans and cis, and this becomes really important for alkenes. Around the double bond, if you have 2 things that are the same, so let's say it's the methyl groups there, those CH3s. Notice in trans, the methyl groups are on opposite carbons, but one is like up and one is like down. In the cis form, you also have 2 methyl groups. They're on opposite carbons, but they're both facing the same way. Like in the way I have this drawn, they're both down, but I could have just as well drawn it with both of them up because these things are rotating all the time. Double bonds don't rotate in solution, so it's very difficult to turn a trans into a cis-2-butene or cis-2-butene back into trans-2-butene. So both of these are actually pretty stable and they stick around really well. Now a trans compound is usually less polar than a cis compound, so sometimes your reactivity will vary a lot if you're using cis versus trans. You only use cis and trans if two of the things are the same around the double bond. In the 1-butene, all right, in the 1-butene, you had 1, 2, 3 hydrogens. So that's not going to have cis and trans. It's only if you have 2 and only 2 things the same around the double bond. So all 3 of these, 1-butene, trans 2-butene, cis 2-butene, they're all isomers. They all have the same number of carbons and hydrogens. There isn't a 3-butene. 3-butene, if you counted in 1-butene from right to left, it would be 1, 2, 3. See how the double bond starts, quote unquote, the third one? Well, that's lame. You should also count left to right, and left to right you get 1-butene. So 3-butene would be like the uneducated way, if you will, of calling 1-butene. Oh, joy. If you have 2 double bonds, you can also have a diene, which just means 2 double bonds. So notice in that structure on the right, that's also a 4-carbon, like a butane, but this isn't just a butene, this is a butadiene, which means 2 double bonds. They start at the first carbon and the third carbon. A butadiene just means 2 carbons. So diene would be 2 double bonds, triene would be 3, etc., etc. But look for the ENE. The ENE is enough to make it a double bond, and again, double bonds are more reactive. But why stop at the double bond? An alkyne is when you have essentially alkane carbons, but there's a triple bond between them. Triple bonds usually have more energy. They're sometimes a little bit more stable, but there is some pretty interesting kind of stuff you can do with these. So an alkyne is just a bunch of carbons, but there's a triple bond in there somewhere. The simplest of all the alkynes is this one in the lower left. Notice that this is a 2-carbon system with a triple bond between it. So if it was an alkane, you would call it ethane, but this is not an alkane. This is an alkyne with a triple bond. So the ethane is turned to ethyne, and you're good to go. Ethyne is actually pretty common. It's also more commonly known as acetylene. So people with torches that weld, they're usually using acetylene in their torches and stuff like that. If you move on to the bute again system, like we looked at earlier a little bit, you can have a 1-butyne where the triple bond starts at the first carbon. You can also have a 2-butyne, all right? So 2-butyne just means the double bond starts at the second carbon. And again, under it is the new way, but1-ine, but2-ine, and again, you'll probably see that if you take organic chemistry. There wouldn't be a 3-butyne. 3-butyne, if you look at it, would be the same as 1-butyne, and 1-butyne is better. Now, in the kind of middle right lower part there's a compound, 4-methyl-1-hexyne. And this is another way you're going to see organic chemicals. This is what they call sometimes a line drawing, and every vertice is a carbon. So what I'm going to do here is I'm going to add where the carbons are. This is a carbon, and this is a carbon, 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 all right? And if you find the longest chain of carbon atoms, you're going to see that this one right here is the longest chain. And that's 1, 2, 3, 4, 5, 6 carbons, all right? So this one would be a hexyne, and the triple bond is always important because triple bonds are more interesting than regular boring single bonds. So that would be 1-hexyne. The 1 is again where the triple bond starts, 1 right there, 2, 3, 4. This is a methyl group. That's off the 4th carbon, 4-methyl-1-hexyne. So again, it's kind of weird, but each one of those vertices right there is a carbon atom. And we saw how lone pairs aren't being shown. Well, now we're not even showing hydrogens at all, and not even really that much with carbons. But you can still figure it out. Carbon needs to have 4 bonds around it. So like the first carbon there on the end, it has a triple bond. there must be like one hydrogen right there. Okay. Carbon number 2 has 4 bonds. It's got a triple on one side and a single on the other. No hydrogens there. Carbon number 3 would have this one right there. That would have 2 hydrogens, etc., etc. So you'll get used to it. This is something you'll see more and more. It's just a way to make these more complicated structures a little bit easier. So nothing you can't handle. And again, trying to introduce this to you before you take the actual class and get snowed over, which is what happened to me. Oh, joy. Okay, about this time, you're probably ready to start drinking. Or, I mean, you're probably more curious about other families of organic chemicals. That was a bad chemistry joke, sorry. But anyway, alcohol in normal world is usually seen as having bad things. Just say no, kids, stuff like that. But actually, alcohol, besides being something that people consume when they're kind of out on a Friday night or whatever, alcohol is actually a family or class of organic chemicals. And in an alcohol, instead of taking your alkyl group and putting a hydrogen on it like we did with the alkanes, an alcohol means take the alkyl group R and put an OH on the end of it, and that actually is enough to make it an alcohol. And the formula is very similar to alkane but with an oxygen on the end. So to name these is pretty chill. If you take a methyl group and you want to make it into an alcohol, you add that OH part right there. Oxygen likes to have 2 bonds and 2 lone pairs, so this is no big deal at all. So methyl minus the YL plus anol, methanol. Methanol is the simplest of all of the alcohols. Methanol is what in Prohibition times, when people used to drink bad drinking alcohol, the stuff would make them go blind. Methanol is definitely not good for the body. Don't be drinking methanol. Bad news. On the other hand, the drinking alcohol is usually the active ingredient is this ethanol. It stems from the ethyl group. When you add an OH to the end of it, it becomes ethanol. Everclear, which is something you can buy at the liquor store. Everclear is almost pure ethanol. Not quite, but pretty close to it and stuff, which is kind of interesting. Propanol would be the propyl group with an OH on it, but there's a choice when you get to propanol where the OH goes. So this one has 2 isomers like some of the other ones we've seen. If the OH is off the end carbon, all right, either the far end left or the far right, either way, it becomes 1-propanol. On the other hand, you can put the OH off the middle carbon, and that becomes 2-propanol. So notice the number shows you where the OH part is on the alcohol, and these are isomers again. All right, they've got different polarities, all that kind of stuff. If you've ever been to the store and bought isopropanol, all right, isopropanol or isopropyl alcohol, that's just a common name for 2-propanol in my world. Alcohols are pretty cool because sometimes, because the polarities are different, they will dissolve chemicals that, for example, water won't. So having a good alcohol is important in my world. I'm just saying no, kids, all right? Not necessarily for drinking. Most of these in the lab you wouldn't want to even consider drinking. Methanol would make you go blind, for example. But on the other hand, they are good for solvents, for making reactions. There's more you can do with alcohols than you can with the alkanes. The alcohol had an OH on the end, but you can also have something which is very similar called an ether. An ether is where you have an oxygen between 2 alkyl groups. So notice this formula, it's ROR. The oxygen is literally between 2 alkyl groups. Now, to name them, it's a little weird. You want to use the smallest alkyl name with an oxy, and then the longer alkane name as an alkane. Now, the most common of all of the ethers is the one right here under the description. And this thing has 2 ethyl groups, 2 CH3CH2s, and again, they're connected by an oxygen. So this is what makes an ether. An ether doesn't have the OH like the alcohol. It's literally an oxygen with alkyl groups on both sides. Now, in this example, there's just 2 ethyl groups, so there's not one that's smaller than the other one, but you want to turn one of the alkyl groups, ideally the smaller one, and give it an oxy name. So ethoxyethane. The ethane is just the normal alkane name, if you will. That would be the official name, if you will, for this. I almost always, though, call this diethyl ether. That's by far a more common name. Diethyl ether is kind of old school ether names. Ethoxyethane is the newer cool name. The one to the right is a better example. This compound has a methyl and an ethyl group, and methyl has just one carbon, so that's shorter, and ethyl has two carbons, so it's longer. So in this case, definitely give the methyl, give it the oxy name. So this would be methoxyethane. Smaller alkane is the oxy, longer alkane is the ane. All right. You could also call this ethyl methyl ether, but that's kind of old school too. I put this one up here because methoxyethane is actually an isomer of propanol. So earlier we saw how there was the alcohols, CH3, CH2, CH2OH was one propanol, and you could have CH3C with a hydrogen and an OH, CH3 being two propanol. Those are both isomers of methoxyethane. There's three different ones, and that's kind of an interesting thing. Here's some more examples. 1-ethoxypropane, 2-ethoxypropane. Again, notice here how the smaller alkyl group is the ethoxy. So in this one, that's where it is, and this is the ethoxy right there. And then there's 1, 2, 3 carbons for the propane. So the first one, the ethoxy is off the first carbon, 1-ethoxypropane. In the second one, the lower one, this would be carbon 1. This is carbon number 2, that weird vertice thing. 3, that would be 2-ethoxypropane. So you can see how the numbering system is really important. 1-ethoxypropane will have different properties than 2-ethoxypropane, etc., etc. A carboxylic acid is actually a pretty common type of group in organic chemistry as well. A carboxylic acid has a carbon with an OH like an alcohol, but the carbon with the OH on it also has a double bond O. So carboxylic acids are introducing us to what's called a carbonyl. A carbonyl is a carbon-oxygen double bond. The fancy name for a carbon connected with an OH, the OH is called a hydroxyl group. So carboxylic acids have one carbon, which is super important. It has a carbonyl, a double bond O, and a hydroxyl group, OH. A lot of things you can do with this. Naming them is pretty chill. You call it like it if it was an alkane. So one carbon would be methane, for example. But if it's a carboxylic acid, you drop the E, becomes methane, and then you add oic acid. So down here, kind of middle left, here is methanoic acid. It's one carbon like methane, but because it has a carbon-oxygen double bond OH, this would be methanoic acid. Methanoic acid has a common name, which is formic acid. Most people call this formic acid and not methanoic acid, but now you know both ways what it is. The even more common acetic or carboxylic acid, is the one in the lower left. This is a 2-carbon system, 2-carbon carboxylic acid group. It's ethanoic acid, but the more common name by far is acetic acid, and we've been kind of playing with acetic acid since Chem 221. It has an acetate group, CH3COO, that hydrogen next to the oxygen. This is actually the acidic hydrogen. Carboxylic acids are a little bit acidic, not super acidic, but a little bit. So when the H plus rolls away, you end up with the acetate, CH3CO2-. It was always weird in Chem 221 to draw acetate because it wasn't CH3CO2- or C2H3O2-, etc., etc. Hopefully you can see now why it's a little bit weird. But anyway, acetic acid is super common. It's the active ingredient in vinegar, for example, so it's something you've probably dealt with before. Propanoic acid would just be a 3-carbon system. The carboxylic acid carbon is always carbon 1. So this would be 1, 2, 3. All right, the carboxylic acid carbon always number 1. Here's some other examples of pentanoic acid, heptanoic acid, but under it I put some different substituents. So this one that I just highlighted, 2-methylpentanoic acid. So again, the carbon with the carboxylic acid is number 1. This is number 2. That's where the methyl group is. 3, 4, 5. That's the pentanoic. The one to the right, again, carbon number 1, carboxylic acid. 2, 3, 4. This methyl group would be the 4-methyl. That would be the 5-pentanoic acid. So you can see how this all works, and you can go on and on. There's heptanoic acid, 7 carbons and stuff. Carboxylic acids are in a lot of the foods we eat, and drinks for that matter. Most of the things we eat and drink are somewhat acidic, so it's okay. You don't have to spit your food out. It's a normal kind of process. Oh, joy. Ketones are a class of compounds that have a carbonyl in them. Now remember, carbonyl is a C double bond O. A ketone is a carbonyl with alkyl groups on both sides of it. So ketones are super important. In the chemistry labs at Maui Community College, we use a lot of propanone. So propanone, the O-N-E, tells you have a ketone. Propane would be a 3-carbon system, but you drop the E, add the O and E, propanone, all right? Propanone, though, is much more commonly known as acetone. Acetone is something you may have in your house right now. Acetone is used to remove paints. It's fingernail polish remover, if that's something you do. So yeah, it's very, very commonly called acetone. Again, nobody except nerdy chemists call it propanone. What am I going to do? Anyway, when you get to pentanone, your carbonyl needs a numbers on it. So you can see here, these are examples of 2 and 3 pentanone. These are both 5 carbons, pentane, all right, but 5 carbon ketones because the O-N-E, but the carbonyl in 2-pentanone is off the 2nd carbon. If you count right to left, it's 2nd. If you count left to right, 1, 2, 3, 4, it would look like 4-pentanone. Don't call it 4-pentanone. Smallest number, longest chain. 2-pentanone would be the best one. On the other hand, 3-pentanone, that carbonyl is off the middle 3rd carbon. That's why it is. Now, ketones, though, are different from what's called an aldehyde. An aldehyde is also when you have a carbonyl, but this carbonyl in an aldehyde has at least 1 hydrogen connected to it. And believe it or not, the presence of a hydrogen next to a carbonyl affects the reactivity quite a bit. So aldehydes and ketones, a lot of times they're isomers, and you got to think about stuff like that, but oh man, look for the hydrogen connected to the carbonyl. The simplest aldehyde is methanal. So if this was a 1 carbon, it would be methane as an alkane. However, this carbonyl has at least 1, actually 2 hydrogens connected to the C double bond O. That makes it an aldehyde. This becomes methanal. And methanal and methanol, the alcohol with 1 carbon, are different compounds. And that kind of blew my brain because it took me a while to figure that out. I'm letting you know. So I'm going to tell you methanal, methanol, different compounds, okay? Methanal is a formal name. Most people call methanal formaldehyde. So at Mount Hood Community College in the funeral services area, they're using formaldehyde solutions for lots of different things as they prepare the bodies and jazz like that. Most people don't call it methanal, but that is the official name. Ethanal would be an ethane aldehyde. Here's the carbonyl with the hydrogen next to it. All right, so it's ethanal. Ethanal is also known as acetaldehyde. Acetaldehyde is something you'll probably use in organic chemistry. We don't talk about it too much in the 220 series, but in organic chemistry, acetaldehyde is something you'll probably use. Anyway, here's propanal, 3 carbons, a carbonyl, and again, carbonyl on the end with a hydrogen, and here's even pentanal. Pentanal would be 5 carbons, carbonyl with a hydrogen. No numbers are needed here because, again, the aldehyde is on the end carbon, so it's all good. But do realize aldehydes and ketones, very similar to each other. Same formula a lot of times, but it's where the carbonyl is. If the carbonyl has a hydrogen, it's an aldehyde. If the carbonyl has carbons on both sides, ketone. An aromatic compound is another thing I just want to touch bases on here a little bit. Aromaticity is when a molecule has extra stability because of resonating electrons. And there's a lot to that statement that we're not going to talk about in Chem 222. But we will talk about the most common, in my opinion, aromatic compound. And that compound is called benzene. Now, remembering that each vertice is a carbon, all three of these structures are the same thing. So the one on the far right, carbon, 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 it's a 6-carbon chain. The one on the far left, we've seen each vertice is a carbon, so you can put the carbons in there. And again, if you're missing a bond, you can put a hydrogen on there. But the one in the middle is a special form where you have a 6-carbon ring and a circle in the middle of it. And that circle represents the aromaticity. And again, that makes the molecule extra special. So benzene is actually a type of compound unto itself. It's not like an alkene or a triene. There's lots of things that benzene and other aromatic compounds will do that other compounds will not. So benzene is what we're going to focus on in Chem 222. And benzene is literally this 6-membered carbon alternating double, single, double, single, double, single bonds. They resonate like crazy to make benzene. If you take off one of the hydrogens and you put a methyl group where the hydrogen was, then you would call this methylbenzene. All right, you're literally putting a methyl group on the end of a benzene. Methylbenzene's common name is toluene. Toluene is a great paint thinner and stuff like that. Instead of a methyl group, if you put a chlorine on it, it would be chlorobenzene. All right. If you have 2 chloros or 2 methyls or 2 of anything, there is a special nomenclature we need to talk about here real fast. The way I would normally call these is I would use numbers. I would say that the first one, the first dichlorobenzene would be 1,2-dichlorobenzene. The next one would be 1,3-dichlorobenzene. And the last one would be 1,4-dichlorobenzene. However, there is a system which is still used a lot, the ortho, meta, para system. And this is for if you have 2 substituents on a benzene ring that are the same. So if there's 2 pieces that are the same or in the 1,2 position, you can also call this ortho-dichlorobenzene. And if they're 1,3 like the middle one, meta-dichlorobenzene. And the last one, 1,4, would be para-dichlorobenzene. And again, they don't have to be chlorines. They could be methyl groups. You could have 1,2-dimethylbenzene or ortho-dimethylbenzene, etc., etc. You can use them either way. This one right here in the kind of lower middle is kind of cool in a juvenile way. This is a methyl group, all right? And there are 3 nitro groups. A nitro is NO2. So the positions, if the methyl group is 1, it would be 2, 3, 4, 5, 6. This compound would officially be called 2,4,6 trinitro, 3 nitro groups, toluene. Toluene is methylbenzene. But almost everybody calls this TNT, all right? TNT, trinitrotoluene. That's where TNT comes from. This is a super explosive. You don't want to mess around with it, but at least you can interpret the Lewis structure / organic chemistry structure in the comfort of your own home and know what TNT is. I need to grow up, I know. But anyway, an amine is also worth talking about. Now, an amine is an example of an organic chemical with a nitrogen. And nitrogen, as you've probably seen from the Lewis structures, nitrogen often has a lone pair and 3 pieces around it. All right? So the simplest of all the amines, which is this kind, is when you don't have any alkyl groups at all. All right? X is 0 in that formula. NH3 is ammonia, all right? And ammonia is a weak base, all right, like all of these are. Nitrogen has the lone pair, 3 hydrogens. But what can happen is those nitrogens can be pulled off, if you will, and you can put something, for example, like a methyl group on it. No problem. So this becomes an amine. An amine is a nitrogen with at least an alkyl group. This is methylamine, all right? But there's no reason to have just one. You could also have two methyl groups. So notice they pulled another hydrogen off and put a second CH3 in. This would be dimethylamine. And if you pull all of the hydrogens off and replace them all with methyl groups, that becomes trimethylamine. So most of the time, these amines, at least for us in Chem 222, it's going to be alkylamine, maybe dialkylamine. If you had a methyl and an ethyl, no problem. You can absolutely do that. Put the substituents in alphabetical order. Eth before meth, E before M. So this would be ethyl methylamine. All right, ethyl comes before methyl alphabetically, but still got the lone pair. Pyridine is real nasty stuff. That would be an aromatic amine. You don't need to worry about that, but I'm showing it in there. Pyridine is actually a fairly common kind of a solvent. Amines are great weak bases. They complement the carboxylic acids we talked about earlier, which are weak acids. But man, amines usually smell really, really bad. So I've tried to stay away from most of the amines. But anyway, if you do the amines, it's totally fine. Just use a fume hood all the time. Oh, joy. This kind of went over the big classes of this organic chemistry lab. And again, we're just looking at the nomenclature of the common ones. There's a lot more to all of these things that you'll learn about in the full year organic chemistry class. While you're doing this lab, all right, you're going to run into some names that will be at first like, what the? All right. Well, first of all, many of the structures can be found in the introductory part of the organic chemistry lab. So if you see a weird name like benzoic acid, I think is one you run into, that structure is actually in the intro pages of the OChem lab. So look through that, all right? And then if you get stuck, a lot of times you'll be able to find the structure in that part of the lab. The alkyl groups are the key for all of this, all right? The alkane, so methyl became methane and methanol and methanal, et cetera, et cetera. So make sure you know those and stuff. The nomenclature guide has also little examples of these different families inside there. So it's got examples of ketones and alkynes and stuff like that if you need to. So definitely check it out. Spend a little time with it and stuff, and you can totally do this. And then if you take organic chemistry, you will be definitely ahead of most of the people in the class, and that'll be really cool. On the other hand, if you don't take organic chemistry, you're still going to recognize a lot of things around you with a lot more detail too. I think it will help as well. Good luck with your lab. Thank you for spending your time with me. I really appreciate it. If you have questions on anything, reach out to me or reach out to the Learning Success Center, Avid Center. We're all here to help you. Good luck with your lab.